Now, usually when you're working with the divergence theorem, you don't actually calculate both sides and verify they're the same. But the idea is that you can take what's the complicated integral and use the divergence theorem to change it, or to change it into an equivalent integral, which is easier to evaluate. Let's do an example like that. Let's let Q be the solid in the first octant, which is bounded by the coordinate planes, and also by the planes x equals 6 and y plus z equals 4. We're going to let S be its boundary surface oriented outward, and we're going to let F be the vector field, x e to the z, y e to the z, and e to the z. And we want to use the divergence theorem to find the integral over the surface. So what we should already be thinking is that we're going to be changing this into the triple integral over the solid Q itself of the divergence of F dv. In the previous videos, when we did example 1, we saw that it took maybe 4 or 5 times as much time to calculate the integrals over the surfaces as it did to find the integral over the interior. So let's begin by figuring out what the shape looks like, and then we can erase a bunch of this stuff and carry out the integral. So first of all, we're working in the first octant, so I can feel comfortable just drawing this part for positive axes. Y plus z equals 4, it kind of appears to be just the line in the yz plane that has x-intercept and y-intercept of 4. But remember that since the x is not specified, I'm going to translate copies of this line parallel to the x-axis. So we actually get a tilted plane that looks like that. Now that plane continues forever in both directions, but I actually want to cut it off on the left side by the xz plane. So it has a wall here. It's cut off below by the xy plane, z equals 0. So it's cut here. And it's also cut off on the back by x equals 0, the yz plane, and on the front by the plane x equals 6. So it's not an awesome picture, but the picture you should have in mind is a triangular prism. So triangular faces on the front and back, rectangles on the remaining 3 sides. So if you did count the faces, notice that there's a rectangle on the bottom, one on the back left side, and one slanted rectangle. And you also have a triangle on each side. So if you were to carry out this integral the way it says, the integral over s of f dot ds, you would have to carry out 5 different integrals and add them together. Whereas if you want to integrate over the solid, you just have to integrate over the interior Q. And that's going to be way, way, way easier. You just have to do one integral. So now that I've got the picture, the main thing I need to capture are the equations for its sides, and I need to capture the vector field, and then we can erase all this. So other than the coordinate planes, this slanted plane is y plus z equals 4. This face is x equals 6. And our vector field, I'll just copy over, is x e to the z, y e to the z, and e to the z. Let's clear all this stuff up. So according to the divergence theorem, the integral we're asked to find is equivalent to the triple integral over the solid of the divergence of the vector field integrated with respect to volume. So let's calculate the divergence of that vector field. The divergence of f is the derivative with respect to x of the first component, x e to the z, plus the derivative with respect to y of the second component, y e to the z, plus the derivative with respect to z of the third component, e to the z. The derivative with respect to x of x e to the z is e to the z. The derivative with respect to y of y to the z is e to the z. And the derivative with respect to z of e to the z is e to the z. So the divergence is 3 e to the z. So we're trying to find the triple integral over q of 3 e to the z dv. Now there's no part about this that looks like a cylinder or looks like a sphere, so I'm not going to use either of those. I'm just going to use regular old rectangular coordinates. And in rectangular coordinates, dv is simply dx, dy, dz. So I'm going to factor the 3 out front. I'll leave e to the z inside. And then I'm going to put dz on the inside. And I'll make a choice about the dx and dy in a minute. So I've captured my divergence correctly this time. If I'm putting z on the inside, then to set up the bounds, I want to send up a line parallel to the z-axis. So the first surface it's going to encounter is the xy plane, z equals 0. Then it's going to continue up on the interior of this solid until it hits the slanted plane. And the slanted plane is y plus z equals 4. In other words, z equals 4 minus y. So to set up my bounds with respect to z, I'll be going from z equals 0 to z equals 4 minus y. And now, let's take the solid and look at its shadow in the xy plane. Well, orienting my axes kind of the way they appear here, where this would be positive y and this would be positive x. Notice that the shadow in the xy plane is a rectangle that goes out to 4 in the y direction and 6 in the x direction. So it doesn't really matter since I'm integrating over a rectangle. I can do dx dy, where x goes from 0 to 6, y goes from 0 to 4. So now let's integrate. Notice that even though the integrand is a product of a function of x, a function of y, and a function of z, our bounds are not all constants. So I can't get away with the writing this as a product of 3 integrals. So let's just work our way from the inside out. First of all, the integral of e to the z with respect to z is e to the z. And that's going to go from z equals 0 to z equals 4 minus y. And plug in the endpoints and subtract. Plugging in the top endpoint, I get e to the e to the 4 minus y minus, plugging in z equals 0, I get e to the 0, which is 1. Don't lose that 1. A lot of the time when you plug in the bottom endpoint of 0, you get a 0 out, but not this time. E to the 0 equals 1. Next, I integrate with respect to x. This is all treated as a constant. There are no x's in here. So I just end up with x times e to the 4 minus y minus 1, taken from x equals 0 to x equals 6. Plugging in the endpoints and subtracting, first of all, I get 6 times e to the 4 minus y minus 1 minus, this time when I plug in x equals 0, I do get 0. And I can factor this 6 in front and multiply it by the 3 to get 18 out here. So I have 18 integral from 0 to 4 of e to the 4 minus y minus 1. Now to continue, I need to do a u substitution where I let u equal this exponent. So let's let u equal 4 minus y, so that du is negative dy. So I'll multiply by a negative 1 right here, so that I have a negative 1 dy, and multiply by another negative outside to cancel that. So I have negative 18 times the integral of e to the u minus 1 du. And notice that as when y equals 0, u equals 4. And when y equals 4, u is 0. So if y goes from 0 to 4, that's the same as u going from 4 to 0. And that might look bizarre to you. It looks a little bizarre to me to have the 4 on the bottom. So let's swap those and change the sign of the integral. Okay, now we can carry out the integral. We have 18 times the integral of e to the u minus 1 is e to the u minus u. And I'll be going from u equals 0 to u equals 4. And then let's start plugging in. Oops. I have 18 times e to the 4 minus 4 minus 18 e to the 0 minus 0, where of course e to the 0 is 1. So factoring out the 18, I have e to the 4th minus 4 minus 1, which is 18 times e to the 4th minus 5. And that's the integral. It was a fair amount of work, but nowhere nearly as much work as it would have been had we carried out those 5 surface integrals separately.